Hello everyone. In this video, we will study cycloalkanes. We will see their structures, stabilities, Bayer's strain theory and its limitations, Coulson and Moffitt's modification of the strain theory, Sachse Mohr's theory, which is also known as theory of strainless rings. Out of all the structures in organic chemistry, cycloalkanes are the easiest to draw because you will see they assume shapes of the things which you see in your everyday life. So what are cycloalkanes? They are nothing but alkanes, but their ends are joined to form a cyclic ring. Like cyclopropane, we have a straight chain propane. Two ends are joined to form a triangle. Similarly, cyclobutane will be a square, cyclopentane a five-membered pentagon, cyclohexane will be hexagon. So because two ends are joined, there is loss of two hydrogens to form that extra bond. All bonds are single. So they have a formula CnH2n. Whatever is the number of carbon atoms, twice will be the number of hydrogen atoms. So in cyclohexane, it should be C6H12. Number of hydrogens being exactly double of that of carbon. And because of these shapes, you can see drawing their structures, you need not to draw every time all the carbons and hydrogens. You can just draw a triangle for cyclopropane. It is assumed that at the point of intersection of these lines, there exists carbon. And carbon will be possessing those many hydrogens which are necessary to fulfill the valency. So think about this carbon. It is having two bonds. Because carbon's valency is 4, it means two bonds are occupied over here. So rest, it should be having two hydrogens. So each carbon has two hydrogens unless it is substituted. So they assume shapes like triangle, square, pentagon, hexagon and higher derivatives. They assume shape of the circle. Their nomenclature is also easy. You can see. Now this is a cyclopentane to which there is ethyl substitution. So the simplest name is ethyl cyclopentane. If there is only one substitution, you need not to number it. Like here methyl cyclopropane. Number is not needed. But if there are two substitutions, then you need to designate the substituent by the number. So it will become 1,2-dimethyl cyclopentane. Or if both the methyl groups are at the same position, then 1,1-dimethyl cyclobutane. So numbering is always given with a objective that substituent, the carbon which is holding the substituent will get the lowest number. Even there can be substitution with the functional groups like cyclopentanone or any acid or ether substitution also. So there are members in the series like cyclopropane, cyclobutane, cyclopentane, cyclohexane. Further, it can be continued as cycloheptane or cyclooctane, nonane. In pharmacy, particularly, the drugs contain maximum 6 or 7 membered rings. So cyclopropane and butane, these are gases at room temperature. You can see the boiling point. So they are gases and rest are liquids. Melting and boiling point, it increases with increase in the series, that is increase in the molecular weight. Because they are containing only carbon and hydrogen, they are highly organic in nature. So they are insoluble in the water, but they are soluble in the semi-polar and non-polar solvents like ethanol and ether. Now let's talk about their stabilities. Because cycloalkanes can exist in different forms, it is very important to study stability of each and every form. And if you relate it to the human beings, you know stability and stress will not coexist. If a person is having a lot of stress, it won't be stable. But if it is able to get relaxed, then obviously it will become stable. Same is true with the rings. If they have a lot of stress, they will be unstable and they won't be favored. They will try to open up. They will try to form a straight chain compound rather than forced being in a ring. But if any form is able to relax itself, then it will try to exist in that form. Most of the time compound will exist in that form. Very first theory in this regard was put forth by Adolf Baeyer in 1885. Just now we talked about stress in the human beings. So the kind of stress which exists in the cycloalkanes is called as strain. And because Baeyer proposed this theory, it is known as Baeyer's strain theory. Baeyer was also known for his another outstanding contributions to the science. He also received Nobel Prize. So one of his such contribution to science includes Bayer's strain theory. He related cycloalkanes with alkanes as both of them contain sp3 hybridized carbon atom, which normally maintains tetrahedral angle of 109 degrees in all the bonds. Exact is 109.28 degrees, or you can round it off to 109.5 degrees. So he simply put forth the theory saying stability of these cyclic compounds depends upon if they deviate with this normal tetrahedral angle, which is not seen in the compounds which do not contain such rings. So simply alkenes. So whatever angle alkenes are able to maintain, if cyclic compounds deviate from that, then it can lead to decrease in their stability. To put it more simple, he calculated amount of deviation from the normal bond angle, irrespective of the sign. Greater the deviation, greater is the strain, lesser is the stability. He assumed that all rings are planar, means all the carbon atoms, they lie in one plane. Like we draw the structure on two-dimensional paper. All carbons, they lie in one plane. So based upon his calculations, he concluded that 3 and 4 membered, that is cyclopropane and cyclobutane, there exists strain, so they are unstable. 5 cyclopentane is stable, but when the ring size increases beyond 6, as the size increases, strain also increases, so these rings are unstable. Let's see cyclopropane. We know it's a triangle, so bond angle is 60 degree. Normal angle was 109 degree. So when we subtract 60 from 109, we get answer 49. So 49 is the total strain. But if you see on each side, out of this normal tetrahedral angle, there is only, it is compressed to give only 60 degrees. So on each side of the bond, there is a deviation of 24, which is half of the 49. So you can write deviation as a total deviation just by subtracting this figure from 109. Answer comes as 49, or you can again divide it by 2 to explain the deviation for each side or for each bond. So cyclopropane has the deviation of 24 degrees, which is quite big deviation. Cyclobutane, it is a square, so bond angle is 90 degree. So total deviation is 19, half of that, so deviation for each bond, it is 9 degrees. Cyclopentane is having deviation of only 1 degree. So deviation for each bond is even half of that. Now, when you draw cyclohexane looking like benzene, bond angle is 120 degree. So Baeyer predicted that cyclohexane should have strain of -5 degrees. Minus sign because now this time this bond angle is more than the normal bond angle. So when you subtract 120 from 109, it will become -5. In case of cycloheptane, strain is even more, what Baeyer predicted. So for each bond, it comes -19. Correspondingly, he also assumed that greater is the strain, that molecule will be unstable, it will be having strain energy. But surprisingly, in this list, you can see, though the deviation is more than cyclopentane, cyclohexane is having strain energy as 0. So this is the limitation of Baeyer strain theory. Even you can see heat of combustion and you can correlate this with the angle strain. So this is just another way of representing. You can either draw it in the form of diagrams to show the actual angles and then deviations, or you can make a table like it was there on the last slide. So Baeyer postulated cyclopropane maximum angle strain, so it should be least stable in all the examples we have seen till now. So because it is least stable, with the slightest trigger, it should undergo easily ring opening, and that is what confirmed practically. Cyclopropane is that way stable in opening the ring rather than compressing it. But cyclobutane, now bond angle has been increased as compared to cyclopropane. So comparatively lesser strain than cyclopropane. So stability is little bit greater, but still there is a deviation. We have seen 9 degrees deviation. So it will undergo ring opening reactions, but not in the slight or dilute conditions. It will need more drastic or stringent condition to carry out ring opening. It will be comparatively more stable than cyclopropane. Cyclopentane, we saw there is only 1 degree deviation. So angle strain is minimum. So it is more stable amongst the one which were there in the table, and it will not undergo ring opening reaction. Well, till this, that is cyclopropane, cyclobutane, cyclopentane, all the postulations which Baeyer did based upon his angle strain theory, they all are true. But when you come to cyclohexane, in the table we saw angle is 120 here and it is 108 here. So according to Baeyer, cyclohexane should have higher angle strain than cyclopentane. It should be less stable and it should be more reactive. And when we go to cycloheptane, cyclooctane, cyclononane, Baeyer postulated that increase in the angle strain should be found and decrease in the reactivity, and even such rings will not exist because of the inherent stability. So these two which are marked in red, these are in fact not true. Baeyer postulated it based upon his theory, but practically it has been seen that these compounds are in fact more stable. So we have important limitations, that Baeyer strain theory is working satisfactorily for reactivity of cyclopropane, cyclobutane and cyclopentane, because whatever he postulated, that cyclopropane is unstable, it will undergo ring opening reaction, cyclobutane will undergo ring opening reaction in the stringent condition, and cyclopentane will not open the ring. That is very correct. But this theory failed to explain the stability of cyclohexane. He proposed that cyclohexane will have more angle strain because the structure on two-dimensional plane shows that angle is 120, which is more than cyclopentane. So it should be unstable and more reactive than cyclopentane. But practically if you see, cyclohexane has zero angle strength and it is more stable than cyclopentane. Baeyer also proposed that larger rings, that is cycloheptane, cyclooctane, they will have more strength and they will be unstable. Even he said that such rings are not possible because they have negative strength. But in fact, such rings exist and they are stable too. And they have lesser and lesser strength as compared to these smaller rings, cyclopropane and cyclobutane. And because of their stability, they do not undergo ring opening reactions. Rings as big as carbon 50, hydrogen 100, they also exist. Even Baeyer assumed that, all these limitations are actually because Baeyer assumed these rings are planar, but this is not true. Because all the carbons actually do not lie in one plane, these higher cycloalkanes are able to retain the tetrahedral angle, and that is why they exist and they are stable. This theory was little bit modified by Coulson and Moffitt. So they went beyond just bond angle deviations. They explained the stability of cycloalkanes through overlapping of orbitals. Because whenever a covalent bond is formed, it is always through the overlapping of orbitals. In case of cycloalkanes, we know all carbons are sp3 hybridized. So Coulson and Moffitt, they proposed that if there is greater extent of overlapping, stronger is the bond. But if overlapping anyhow decreases, then compound and the corresponding bond will turn weaker. In sp3 hybridized orbitals, they usually overlap by end to end. So there is end to end overlap. Pi bonds usually overlap laterally. So sigma bonds are formed because of end to end overlapping in this case of sp3 hybridized orbitals. So this is a good overlap, but by any means, like because of compressing the bond angle in case of cyclopropane. If there is poor overlap, you can see this overlapped area, then bond is weak, compound is weak. So here comes the concept of bent bond or banana bond. Even this modification is also called as molecular orbital theory. Imagine a propane which is free because it's a straight chain compound. So there are three carbons. So this is first carbon, this is second, and this is third. These are sp3 orbitals, and you can see the overlapping compound can arrange itself in order to have maximum overlapping. Bond angle of 109 is maintained. The moment we try to fit this propane as a cyclopropane, now you can see three carbons are forced to come close to each other. So these two carbons, you can imagine like they are pulled towards each other. So these bond angles are forced to compress. Now you can see now there is no enough space for complete overlapping. So instead of overlapping in a straight end-to-end overlap, you can see it has the orbitals change their shape, still trying to overlap maximum, but because of the restricted distance between this, there is poor overlapping on all the sides. So instead of bonds being straight and strong, these bonds are bent. It resembles shape of banana. That's why it is called as banana bond theory. So Coulson and Moffitt's this modification explains why cyclopropane is unstable. Even same thing was put forth in Baeyer's theory, but it was in the concept of deviating in the bond angle. More the deviation, unstable it is. But this theory explains it in terms of orbital overlapping, causing a bond to be strong or weak. So because it is a compressed molecule, there is no complete overlapping of the orbitals to form sigma bond. That is why bonds are called to be bent or banana shaped. We have seen limitations of the Baeyer string theory. That theory was applicable to only lower cycloalkanes like cyclopropane, cyclobutane and cyclopentane. But the moment we try to make it applicable to cyclohexane and higher cycloalkanes, theory doesn't work. Sachse in 1893 and Mohr in 1918, who actually refined the theory put forth by Sachse. So together this theory is known as Sachse Mohr theory. This theory helped a lot to prove stability of higher cycloalkanes, which is observed practically. They proposed that because it was predicted by Baeyer, there is a strain, so they are unstable. So Sachse and Mohr proposed that such rings, they are free from strain because all the ring carbons, they are not forced to be a part of one plane. Rings assume themselves folded or puckered situations which can maintain tetrahedral angle of 109, that is the normal tetrahedral angle, and thus strain is relieved and these rings are in fact stable, they exist. But there are various forms in which they exist. These are called as conformations and all are single bonds. So these conformations are easily interconvertible to each other just by rotation of the bonds. If we take example of cyclohexane, it exists in two conformations, chair and boat. Chair because it resembles a chair on which we can sit. Boat because it resembles shapes of the boat. There are many in-between conformations like half chair, twist boat, which take place during conversion of one chair to another chair form. So in this cyclohexane, rather than all 6 carbons in one plane, 4 carbon atoms. See this one, 2, 3 and 4. 4 carbon atoms lie in one plane. Now remaining 2, if they are in one plane, it is boat. If one is above the plane, other is below the plane. Here it is just reverse. This one is above, this one is below. Then it is called as chair conformation. And this is more stable because you can see these two are far away from each other. So their hydrogens won't interact. As in case of boat conformation, both can come close to each other and they can create steric hindrance. So chair form is more stable. I would recommend you all to visit this website. I will put this link in the description box. If you go on this website, you can see a three-dimensional representation of cyclohexane like we draw it in the 2D form, and you can literally play with it to convert it into chair, boat, and you can have different models to be generated out of it. Every carbon in the cyclohexane contains 2 hydrogens. One of that is axial and another is equatorial. So axial hydrogens are those which are coming from the bonds which point straight up or down. See, all indicated by black. You will observe every time either this is straight up or it is straight down. Here it is straight down, this is straight up, and if you notice carefully, it is alternate. up, then down, up, then down. Similarly, equatorial, they are also up and downs, but these are slightly above or below the plane. So this is the first, because axial is up, equatorial is down, but you will not draw a straight line. Equatorial are slightly below or above the plane. So this is projecting below. Now imagine this second carbon atom. It is having axial down. So equatorial is up, but it is projecting slightly up. Third, axial is up, so equatorial is down. Fourth, axial is down, so equatorial is up. You can draw chair conformation in this sequence. You need to draw two parallel lines. You can draw it in another opposite direction. You will get another chair form. So draw two lines which are parallel. They indicate four carbon atoms. At the corners, four carbon atoms will lie in one plane. Now you just need to join them. That will create a carbon which is above the plane. On opposite side, if you join them, it will create a carbon which is below the plane. And for drawing hydrogens, start from any one end. But remember to draw up, that is this first axial hydrogen is up because this carbon is up. This carbon is above the plane. That is why axial is drawn up. Now second, now you need to follow alternate. If this is drawn up, this should be down. So this axial bond is down. Now third, it should be up. Fourth should be down. Fifth should be up. Sixth should be down. Now while drawing axial bonds, it is very easy because it is simply up and down straight lines. But in case of equatorial lines, this first is up, so we have to draw it down. Now it should be tilted slightly, and it's always better to correlate it with some other bond. It will always be parallel to some other bond. Like this bond is now parallel to this bond between C5 and C6. Or if you are numbering from this side, then C2 and C3. It is parallel to this. If you take up this second one, axial was down, so we need to draw it up. So it should be tilted in a way. It is parallel to this bond C1, C2 or C1, C6, the way you want to number it. Now imagine this third. This is up, so we need to draw it down. You can see a Z shape over here because this is parallel to this one. Similarly, this will be there. You can find out to which bond it is parallel. C5, again you can correlate which bond it is parallel to. And lastly, because this was down, this is up. So this is all about drawing cyclohexane correct chair form and giving axial and equatorial hydrogens. Similar conformations can exist in the higher cycloalkanes. Baeyer had postulated that these rings will be having too much of negative strain and they won't be possible to exist, but Sachse Mohr theory explains that they can exist and they can choose in which form they can exist. Like cyclohexane was chair and boat. If you look at cyclooctane, it can be a combination of chair and boat, chair and chair, boat and boat. Because chair form was most stable, we have seen. Here also chair is more stable. Boat is highly unstable. If you look at this chair boat, intermediate stability, see on one side it is chair. Now in case of cyclohexane we will immediately join it to complete a chair. But because this is a combination, now half part is chair and to which a boat is attached. So this is a chair boat conformation. Similarly cyclodecane, it can have boat. See, this is a downward boat. chair in between, and this is a straight boat. Or there can be chair, chair, chair. It can look like a step, or you can see shape of W over here. One side it is W, another side it is M, capital M and capital W. So such higher cycloalkanes exist in such conformations, and they are easily interconvertible to each other just by rotation of the bonds, even at room temperature. And they will try to exist in the form which is more stable. So this is all about cycloalkanes, their introduction and their stability. These are some sources from which images have been taken, and you can visit this website CameTube 3D, and you can enjoy playing with cyclohexane, converting their different conformations to each other. Next in this series we are going to see reactions of cyclobutane and cyclopropane. So until then, take care, goodbye.